Yes, I'd like to try to show you a little bit on what we could call power and sample size considerations. And this can be a little bit of a difficult concept for many people, but let me talk about power and show you what some people would call the magic sample size formula. I'll do it in a context, and then just one context, and the context I'm in is the one sample situation. So I would think about the situation where we're going to perform an experiment with just a single sample of data, and we are interested in something related to the mean. So the hypothesis would be that the mean, mu, equals some mu 0, and then I choose for the concept, I choose a one-sided alternative. I mean, this can be done in any situation, but we need to decide on one situation. So I'd like to show you this in the context of a one-tailed hypothesis test with an alternative to the right of mu 0. So we would like to perform a test, hypothesis test, to try to prove that mu is larger than mu 0. Now, what we should then, before we do such an experiment, we could raise the question, actually, when we're in the planning phase: how large should I choose to make this experiment? How large is sample size? That's the sample size, right? How large should the sample size be? Well, to answer this question, we should be able to consider what we call the power of the test. So this is something we use in the planning phase. What is the power of a hypothesis test? The power of a hypothesis test is the probability, I'll write it in words here, probability of rejecting the null when we should. I mean, when the alternative is really true. That's spelled out in words. The probability of actually detecting something if it's there, that's the power of a hypothesis test. This is something we'd like to be large, right? We'd like to be able to detect when we should reject, right? That is a good thing. Now, the challenge of the concept of power is that this is actually a function of the true mu. That is, if we put out the scenario that mu is actually larger than mu 0, that's then the situations where we should reject, right? However, if mu is very much larger than mu 0, maybe it's easy to find out, to detect that. And if mu is close to mu 0, probably maybe it's more difficult to have an experiment finding out about it. So the power of an experiment depends, unfortunately, on the true state out there, which we don't know. So when we talk about power and sample size, it will be some kind of scenario-based thinking, but it's an important scenario-based thinking here. We can actually do it in this context. We can actually find the power. We can find the power in this case. So I'd like to now assume that we have a true mu. Let me see. We have a true mu1, which is actually larger than mu 0, right? Which means that, sorry about my confusion here. Let's try to see if we can find the power in this case. I'm telling you that power is the probability of rejection. When do we reject the classical null hypothesis here? We reject, and now I base it on the set statistics. We will reject, we're going to make a classic sort of sketch plot here. Let me do it here. Here we have the 0. We shouldn't be too close to do it here. Here's the 0 distribution. I reject in a one-tailed case. Here is you could say the rejection. Let me put it out here. This is the rejection area. We reject a hypothesis test if the observed difference between the data and the null hypothesis divided by sigma over root n. We take the version with the known sigma for this consideration here. If this one is actually larger than the critical value set alpha, right? If we're out here, we reject, right? When the test statistics is larger than the critical value, then we reject. So the question is, what if we have a true situation where, now this is kind of a distribution over here for sort of x bar minus mu, right? What if the true distribution is really mu1, right? If the true mean is not mu0, but something bigger, so that's the assumption of the being in the alternative, then I'll just sketch it somewhere to the right of it here, like this. The variance should be the same here, not a good sketch, but still. What if I'm really at mu1 minus mu0 here for the difference? What if I'm really out here? What is then we could say, what is the probability of rejection in this case? Well, we should actually try to, using this distribution, trying to find out what is the probability of actually, in this distribution, being out here. You see, that's much larger, actually. If there really is an effect, the probability of rejecting will be larger. The larger the sort of the difference is, or the larger the mu1, the higher this probability, but we can find it. We can be exact about this. That's the power function. So, since under this situation, we have that x bar minus mu0 would then really have a normal distribution with a mean of mu1 minus mu0 and the same variance as before, that is sigma squared over n. So if we use this normal distribution, we will see that this power probability here actually becomes the same thing as taking, if we use the standardization rule of a usual normal, we can actually see that we should subtract the mean, divide by the standard deviation. So this is like taking the probability for a standard normal of being above this critical value minus the mean of this one, and the mean of this one would then be mu1 minus mu0 over sigma over root n. This is the kind of the mean of this distribution, right? Because it's the mean here, and then we divide by the standard deviation. So this is the power, actually. I just rephrased the power on the standardized scale, actually. So I could compute the power for a certain, if I choose some mu and I play around with some sigma scenario-based, and I choose an alpha, I can compute the power, the probability of rejecting mu1 when I should reject. That was the power. What about the question I asked you in the beginning? What should n be? Now the concept is we should choose n to achieve a certain level of power. I want to make an experiment with a certain probability will find the important things if they are there to find. So that's a scenario-based way of thinking. So what we do will be to say, we want, for instance, we want power equal, usually we call the inverse of the power, the risk of actually not rejecting, we call that the beta. So the power would be 1 minus beta. Often we would say, in classical assumptions, often we would have a risk level of 10%, that is, we want a power of 90%, we want a probability of 90%, maybe, to find the important difference, right? So we would want this probability here that I just found as the power, that is this part here. I want it such that, I mean, the variance of this depends on the n, that's the point. So I can choose it such that this probability here becomes 90% or above by letting n increase, because increasing n will decrease this variance on this plot. So I can get the probability I want just by letting n increase. So I want this probability here, sigma over root n. For instance, I want this to be, let me see, 0.90, for instance, right? And if I go on from there, I'll skip all the details now. If I go on this one, I can actually find that if I exactly equate this one with the set, I have minus set beta, then set alpha, and then I take this one, mu. Actually, there is some sign thing going on here, so I take mu0 minus mu1 here. I believe, actually, it doesn't matter finally, because it's going to be squared. So actually, I'm a bit in doubt about the sign thing here. So let me just say mu1 minus mu0 divided by sigma over root n. This one is going to be, I should have the plus there. And then finally, maybe it should be mu0 minus mu1 actually. The thing is, I'll finish here, it's a bit messy here at the end, but anyway, if you rewrite this expression, if you isolate n in this expression, you will see that you get an expression saying that set beta plus set alpha divided by mu, must be mu1 minus mu0, sorry about that, divided by sigma. All of this squared. We have what is known by some people as the magic sample size formula that tells you that given some alpha level, given some power specification, some wanted power, then speculating, scenario-based on the potential difference that we're facing in relation to the variability, that's the scenario-based. Sometimes that's called the effect size, or the relative effect size. This is, of course, the thing we don't know, but then we can speculate. What if there is an effect size of this? How large a sample size do we need to find this effect size, given the alpha and the beta, that is the type 1 level and the power level? This is actually how we can use first the computation of power, and then we can, by putting some specification on the power that we want, we could transform it into finding the needed sample size to have an experiment that can give us the power that we want to find the differences that are interesting, scenario-based, before we do any experimentation. This is very important in planning phase of experiments, to think about what things can you actually detect with the amount of investment, the sample sizes that you're actually using. So that is the power and sample size considerations exemplified in the one-tailed hypothesis testing for a single mu. Thanks.